Okay, guys, welcome. So today we're going to talk about another type of modeling type of problem where we're going to today look at electrical circuits. So one thing that is interesting to note here about electrical circuits is that this is, it's almost analogous to the mass spring system, and we'll talk about how that's sort of true later. But there are some sort of nice carryovers that we can sort of consider, and we'll do that later on. So this figure here is showing an RLC circuit, which basically means we're looking at resistance, inductance, and capacitance in a particular electrical circuit. And of course, this is a basic building block of large electric networks in computers and other applications, right? So we can show that with Kirchhoff's voltage law, that was the example that we sort of considered in the first order linear ODE setting. But of course, now again, we're going to extend this to a second order type of problem. And we can show that the model for the RLC circuit is given by this, what's called an integral differential equation, right? And of course, it's because it contains both integrals and derivatives, right? Oh, and it even says that down here too. But anyway, so what's going on in this electrical circuit system here is that anytime you see sort of this jagged edge here, that's R, which is like a ohms resistor, which is like resistance. Anytime you sort of see these almost sort of the parallel symbol, but one of those lines is sort of curved there, that's the capacitance. And sort of the squiggly lines there are indicating inductance. Right, so this is what a typical RLC circuit might look like. Okay, so I had mentioned that model that we were given above is an integral differential equation, but to make it into just a regular differential equation, we're going to take the derivative of both sides with respect to t, and that's going to allow us to, now we have gotten rid of the integral, and now of course we have a second order linear non-homogeneous ODE, right? So, and now occasionally we'll also say, and I think this is a typo here, right? I think this should be, so if I is Q prime, then I think that this, not this one should be just a Q prime, right? So I think that's a typo in the notes here. So that's another form that's presented. And of course, we use the relation here that I is equal to Q prime to arrive at that. And that's another way that we can sort of eliminate the integral in the original model. And of course, the advantage of that is that you don't disrupt E of t. Okay, but anyway, so to solve this, what we would need to do, so again, we have a non-homogeneous second order ODE, so your general solution is a combination of the homogeneous solution and the particular solution, right? So to find the solution for this, we can use the method of undetermined coefficients. So again, we can proceed just like we did before, and we can say that our particular solution is going to be of this form. It's going to be a sum of sine and cosine terms. And then we can find each of those derivatives and then plug them into our ODE. And then if we equate the sine and cosine terms, we're going to arrive at these two equations here. Okay, so now, before we solve for A and B, we're going to define this variable S here, which is called the reactance, which is just made up of omega times L minus 1 over omega times C. And again, our L is our inductance, and our C is our capacitance, right? So now, of course, if we substitute in for S into our systems up here, and we plug in, if we divide by omega and then substitute back in for S, we now arrive at these two equations here. Right, so now when we solve each of these, we can solve them with elimination. We can get these two equations here. And now if we solve for A and B, as long as R squared plus S squared, of course, is not 0, we get that A is negative E sub 0 times S over R squared plus S squared, and that B is E0 times R over R squared plus S squared. Okay, so of course this gives us the particular solution if we come back, right, to this here. If we plug in those A's and B's, we get the particular solution that we want for the non-homogeneous ODE. Okay, so now one way that the particular solution is also written is given by this. And again, this is sort of analogous to the other representation of the mass spring system that we looked at before. And then, of course, I0 is given by this quantity here. And then tangent of your theta is equal to S over R, or minus A over B. Right, so that's sort of, that's sort of analogous to the mass spring system. Right, now the square root of R squared plus S squared is called the impedance. And this is also equal to the ratio E0 over I0. Right, and this sort of has a relation, so it's sort of related to Ohm's law. And because of that, we can sometimes also call this, I believe it's the apparent resistance. Okay, so of course a homogeneous solution will look like something like this, because we are looking for the roots of this characteristic equation, of course, once we divide through by L. And you can find that your two roots are negative alpha plus or minus beta. And of course, your alpha is given by R over 2L. And your beta is 1 over 2L times the square root of R squared minus 4L over C. All right, and that's something that you can and should verify. All right, but for time's sake, we're not going to go through it. All right, so of course, now in an actual circuit, your resistance is never fully 0. So what that means is that your homogeneous solution is always going to approach 0, right, as t goes to infinity. So the transient current is always going to approach your steady state current, right? Because again, since IH goes to 0, that means that I, which is IH plus IP, is going to just approach IP. And again, this is your steady state current. Okay, so let's look at an actual example of this. Okay, so in the first example, we're going to find the current in an RLC circuit with a resistance of 11 ohms, 0.1 henries, and 10 to the negative 2 farads. All right, so this is connected to a source where our E of t is 110 times sine of, we're going to use 377t. All right, so we're doing a little bit of rounding here, but this is going to be what I'm going to use. Okay, so, and we're also later, we're going to assume that the current and capacitor charge are 0 when t equals 0. That will help give us our initial conditions later on. Okay, but again, what's the first thing we do? We need to find the general solution of the homogeneous ODE. So the homogeneous ODE will be when our right-hand side is equal to 0. Remember that this is like E prime of T, right? Because we're using the I double prime model. So our homogeneous ODE is, of course, that's now 0, and we get this characteristic equation, and you can find that your two eigenvalues are -10 and -100. So of course your general solution looks something like this. Okay, what do we do next? Now we find the particular solution, I sub p. So first we need to find the reactants, which is S, which we can find by computing omega times L minus 1 over omega times C. Right? And again, remember that your omega is just the inside of your electromotive force, which of course is 377. All right, and then we were also given that L is equal to 0.1 and C is equal to 10 to the, what was it, -2. So that's 100, 1 over 100, right? So if we plug that in, we can find that S will come out to be 37.4. All right, that's just a little bit of algebra plugging in these numbers. Okay, so with that in mind, that means that our particular solution is of the form A times cosine of 377t plus B times sine of 377t. Okay, and of course our A and our B are given by this, which again, with some algebra, we can calculate to be -2.71 and 0.796. Right? So then what does that mean? Well, that means that our general solution is given by our homogeneous solution plus our particular solution that we found with the undetermined coefficients method. Okay, so now what does a particular solution look like for the initial conditions? Well, I of 0 equaling 0 allows us to include this relationship between C2 and C1. So namely, we get C2 is equal to 2.71 minus C1. And then the second initial condition is that Q0 is equal to 0. But here we're going to use the fact that I is equal to Q prime. So this means that the integral of I with respect to T is equal to Q, right? So when T is equal to 0, we get that L times I prime of 0 plus R times 0, 0, which allows us to conclude that I prime of 0 is 0. So now we can find the derivative of I of our solution, right, of our general solution, and that will allow us to conclude that C1 is -0.323 and C2 is 3.033. So once we plug that in, that will give us our particular solution. All right, which of course is a little messy, but now, and depending on how you round it to, you might get something that's completely off, but this is the idea. Okay, now in this case, you actually approach the steady state very quickly, right? And the reason why is because these two terms in your homogeneous part of the solution decay to 0 really quickly, right? Especially because of the e to the -100t term. That's going to approach to 0 very rapidly. And you see now that you're just getting the oscillation from the sine and cosine terms, right? So that's sort of the idea. Okay, now earlier I had mentioned that there is quite a bit of, you know, an analogy between the mass spring system and the electrical circuit system that we're looking at now, right? So if you look at the two ODEs, they're very similar, right? You sort of have this relationship here where they're both second order linear ODEs, and their sort of input force is sinusoidal, right? It's cosine, but it's sinusoidal, right? So you get sort of these relationships which are kind of interesting, and you can see that like the inductance in an electrical system is sort of like the mass in a mechanical system, and then a resistance in an electrical system is sort of like the damping in the mechanical system, right? And then you get that the capacitance is sort of like the spring constant K, and sort of the important one here is that the current is sort of like the displacement, right? Now this of course is just a numbers analogy here. It's not right that electric and mechanics are the same thing, but there is sort of like this relationship here. Okay, so that concludes this video on electrical circuits. So I hope you enjoyed, and I will see you next time.